I accidentally ended that Zoom. I'm glad you guys got back. And here we are, back to our conclusion for chapter 18. Trying to share the screen here. Here we are. Our biggest mechanism in this chapter is the Hofmann rearrangement. And it only works, it's very limited in scope, but very useful nonetheless, because it's a way to make primary amines from primary amides. Only works under those two circumstances. Any other amide, you don't get this reaction. And here's why. We're going to be reacting our primary amide, which has a pKa. We have a new pKa. It looks a lot like an alpha hydrogen, except the H is attached to a more electronegative atom than carbon. Remember, if this was an aldehyde or a ketone, this would be a carbon, pKa 20. So what would be a reasonable guess with an inductive effect that makes it easier to make an N minus than a C minus? And if you go down to pKa 10, you've gone a little too far. 17 is closer to the actual number. So let's make sure we know that's important. Let's see. I don't know. I think it's going to try to straighten it out for me. Did not. Good. So 17 can be taken off with hydroxide, which we're doing in step 1, and then again in step 3. So pay careful attention to these steps, because we're going to do our own version of this reaction on the next page. As you see underneath, there's a mechanism required with the Hofmann rearrangement here and a lot of review stuff for some important comparison reactions. So step 1, acid base to generate an anionic nitrogen. Anionic nitrogen is attacking bromine to make a nitrogen bromine bond, which causes the pKa to be a little less than 17 now, with yet another inductive effect. So 17, but probably a little lower, which means that's the most acidic hydrogen now. And then we generate an O minus via acid base and resonance. That's a combination of things. And then something different happens when this thing tries to resonate back. Instead of just resonating and generating an N minus, the carbon group is shifting from an adjacent carbon, used to be the carbonyl carbon, now it's an imine carbon, and it's rearranging to the nitrogen. So that's a rearrangement step there. Here's our nice short form for a rearrangement step. And the reason rearrangement happens is the nitrogen adjacent has a leaving group on it, and we have generated what's called an isocyanate here. Isocyanates themselves are useful yet dangerous intermediates in synthesis. This isocyanate, under the conditions of this reaction, is going to undergo a hydrolysis. And it's a base-promoted hydrolysis. So let's see what's going on first. And I stopped numbering my steps. In review, acid base for 1, attack of the bromine, nucleophilic attack on the bromine for 2, acid base again for 3, rearrangement for 4, Hydrolysis begins in 5. It's really 5 and 6 if we're combining steps, but this would be 7 and 8, but really we're just going arrow numbers here. And then our final protocol at the end here will generate carbonate ion and an amine that has one less carbon than our original amide. Where'd the carbon go? Well, it's part of carbonate. Overall, the process is viewed as a decarbonylation. I will write that down. You've never heard that word before. Oh, it put a circle. Isn't that nice? Decarbonylation. Cool. And let's see what happened here. Hydroxide attacked the positive carbon. Why is it positive? Well, it has 4 bonds to more electronegative atoms. That would make you feel positive too. And the pi breaks first towards the O. Why? Because O pulls on electrons more strongly than N. So we don't break this pi, although it would make our lives a little more convenient. Electrons resonate in the second step, and we also protonate in the second step. So it looks a little like a tautomerization in the second step, doesn't it? Make a pi, pick up a proton. And then what's going on here is we have a carbamic acid. Carbamic acid here, double star right there. These are not stable species. Normally they would undergo loss of CO2. And that is happening here, but under basic conditions, CO2 will become carbonate. And how's that happening? Well, hydroxide attacks the positive carbon in a second step. First step is, as you would imply with a name that has acid in it and hydroxide present as well, you're doing an acid-base step in black. That would have to happen first. And then the nucleophilic attack second. And then what looks like a tautomerization, but is really an elimination because you're getting rid of a leaving group, hydroxide in this case. Hydroxide's a catalyst. It's used here and made here. And that would generate your carbonate ion with a pi bond here and 2 O minuses. And the amine picks up a proton here as well. So we've got that. I think we can do that mechanism on our own on the next page without assistance from the gray box, the shadow box. We shall see. Down here we have a little scheme, and I like this scheme. It's one of my favorites. You'll see it always shows up on tests where I take an alcohol and I make it into 3 different primary amines. If you look in blue, we have 3 different primary amines. We have one with 1 less carbon. That's when I'm thinking about the Hofmann rearrangement. We have one with the exact same number of carbons, 5. There I'm thinking reduction of an amide using lithium aluminum hydride, which is going to go in that box. And up here, I had to put a new bond to carbon, which we did a little earlier today. We first put a leaving group on the OH position, SOCl2 and pyridine, and then cyanide, SN2 reaction. So on the next page, we'll have all the answers. Here's the nice blank version. And start here. Why don't we do the one we did earlier today? Nope, pen's off. A lot of talking, no writing. PBr3 puts a bromine where you used to have the hydroxyl group. In step 2, KCN. How about another polar aprotic solvent? Optional, you don't have to show the solvent. Dimethyl sulfoxide is a good polar aprotic solvent for the SN2 reaction that you want to do in step 2. How do we reduce a nitrile to a primary amine? We have options. Nitriles are not that polar, so you can use the nonpolar option. You don't even need pressure. Remember, if this was an aldehyde or a ketone, you would have needed pressure. We don't need that here. Or we can use our more versatile and less or more reactive set of conditions. Let's get a new color going here. Lithium aluminum hydride. We can do one more or telephone pole. Here's telephone pole. This is one of the rare circumstances where sodium borohydride does the same thing as lithium aluminum hydride. That happened with aldehydes and ketones as well. That's the only 3 times that sodium borohydride will do the same thing as lithium aluminum hydride. One is clearly right here to make a nitrile into an amine. The other is to make ketones into secondary alcohols. You can use either set of chemicals. Or aldehydes into primary alcohols. You can use either set of chemicals. After that, sodium borohydride only had one more use, and that was way back in chapter 6 when we were getting rid of a mercury. Who remembers that? But lithium aluminum hydride will continue to grow in the arsenal of reductions. So we'll see more from that one later. Now, what reagents can make an alcohol into an amide? Well, remember, amides are called carboxylic acid derivatives for a reason. They come from carboxylic acids. Alcohols are not at the right oxidation state. They need to be first made into a carboxylic acid. And that is accomplished with some kind of chromic acid reaction. Don't forget, you need the water here. Without that AQ, you're going to lose a quarter point. You've got the general idea, but without water, nothing's really going on. You're not generating chromic acid, therefore you're not going to be doing reduction or oxidation. Sorry. Now I need to make a carboxylic acid into a amide, and I don't know how to do that. I do know how to make amides from derivatives of carboxylic acids. Remember, the top derivative is an acid halide. I could work from there. The second derivative is an acid anhydride. I could work from there. The third derivative was an ester. I could also work from there. I would use ammonia in the second step of all of those. Acid halides are easily made, and we can just stick with that one, go with the most reactive derivative. So now you're at the stage where you have a acid halide, and it is time to make an amide, a primary amide. Step 3, NH3. We call it aminolysis. And it makes a primary amide with one more bond to nitrogen than nitrogen had before, one more bond to carbon, that is. And yeah, it's the carbonyl carbon. And then we have to remember that a primary amide can be reduced to a amine with the same number of carbons using our very versatile lithium aluminum hydride. Followed by HCl. You would get 0 points here if you thought that sodium borohydride does this reaction. It does not. This is the only one we learned that does this reaction. Number one mistake I see students make is they say carbonyl is becoming CH2. I'm going to use the Wolff-Kishner reduction. It doesn't work with carboxylic acid derivatives. It only works with aldehydes and ketones. Look back on a couple of videos. I keep saying it over and over. I'm hoping this is the semester nobody tries to do a Wolff-Kishner to get from here to here. And then this is our new reaction where we're using excess hydroxide in the presence of bromine. And I want to remind you that's called the old Hofmann rearrangement. And we're going to do that mechanism here. And we have plenty of time for that. So let's do it. We have an isobutyl group over here to the left of the carbonyl. We should show one of the bonds to the nitrogen to hydrogen, erase the second H there. We need hydroxide. We can just draw it. We do have a lone pair on the nitrogen already. We have bromine. Bromine can be here. And we're going to always do red first and blue second. Acid base first. pKa. What was the pKa for the new primary amide functional group? It was 17. And after you generate an N minus, it's going to hit bromine. So we saved an intermediate from the original text mechanism. And we have an IBU attached to a carbonyl with an N that has a bromine, still has an H. What was next? I think there was another acid base that took advantage of the inductive effect of the bromine here, generated an O minus all the way up to here, and then the rearrangement. If I'm careful, I think I can do this all at one time. We need another hydroxide. And that's going to resonate in. And the O already has a lone pair, so it's going to resonate back. Sigma bond between isobutyl and carbon rearranges. I hate to cross arrows, but it's clear that we're going all the way to the nitrogen, I hope. And now you've got a carbonyl down here, attached to a C. The C has how many bonds to nitrogen? C had one. Now it's getting a second one. I drew it linearly. And the isobutyl used to be bonded to the carbon. Now it's bonded to the nitrogen. And that's an isobutyl isocyanate. And then I believe it's time to hydrolyze this with more hydroxide. There is a large excess of hydroxide in this reaction for a very good reason. Oh, that's weird. I just jumped on the screen somehow, didn't I? All right, let's find our stuff. Is it this one? Yes. Okay. I have a new page with 2 dots on it. We'll get there when we get there. Hydroxide. What's going on? We have hydroxide and isocyanate. Time for a little flashback. Isocyanate, hydroxide, attack carbonyl because it's the most positive species or atom present. Generate O minus, which resonates back and protonates the nitrogen. And we're going to get a carbamic acid. This is a carbamic acid. Hey, if you're stuck, just remember, I got to make a carbamic acid. What's that look like? Looks like a carboxylic acid that has a nitrogen. Kind of looks like a hydration product, doesn't it? New stuff is blue. We can get the OH on by attacking the carbonyl. Break the pi. The lone pair comes back and picks up a proton from the best. Oh, don't do that in red. From the best acid present. What's the best acid present in a reaction involving hydroxide in water? That last word is the answer. Water. Protonation of the pi generates our carbamic acid. So, little reminder here. If it's a mechanism question on a test, I typically try to show this for you as a reminder. That's where your carbonyl needs to go. And how do we get there? It's got a third O on there. How do we get a third O on this carbon right here? If you track it with hydroxide, then you are neglecting the fact that this is a carbamic acid. What should acids do first if there's base present? Are they going to get attacked on the carbonyl or the acidic proton? I think I may have given away the answer. Carbamic acid should act like an acid first. And then the carbonyl can act as an electrophile second. Hydroxide number 2. In this step, we've used many hydroxides. And if we go with green third, I think we can get our carbonyl back. Let's see. We got lone pair. We got green. And we got this thing leaving and protonating at the same time. I believe that gets us to the end. Except for one thing, which I'm really not that concerned about. The way we did the mechanism this time generated bicarbonate, and it also generated our primary amine, which was our goal. Am I going to grade you if you leave it here and don't deprotonate to the conjugate base? I'm not going to dock your points at all. If you like our mechanism here, you can stop here. But hydroxide would deprotonate this to make that side product once again. Don't want to belabor the point on side products. And we have this page here to finish up the chapter. And we'll do a brief intro to chapter 19 today, because we need to be finished with all of our material by Wednesday. And I think you know the reason for that. So what we have here is, how do we make an acid anhydride? We haven't learned how to make those yet at all. We can make a carboxylic acid anhydride from a carboxylate. And I want to remind you, a carboxylate is a moderate nucleophile. Remember, it was the only anionic nucleophile that was not strong. And the reason why it wasn't strong was that it was a resonating anion, makes it less reactive, makes it more stable. But an acid halide is a very reactive electrophile, so pretty happy combination. And the mechanism, I don't think we need to do this mechanism together. It's 2 steps. We've been doing these steps all chapter. Attack the carbonyl. The O- then resonates back and kicks off chloride, and you're done. Got a lovely acid anhydride here. And that's the end of that. The only way that we know how to make acid anhydrides. So if you had a retrosynthesis where you made an anhydride, you should be thinking back to the 2 previous things. What were the 2 previous things? They were a carboxylate and an acid halide. You could reverse the order of these 2 and have the carboxylate here, in which case this thing would be the attacker, and the acid halide here, in which case this thing would be the thing attacked. You would get the same result. So there you go. This is something we already did just recently, twice already, today. Cyanide can attack carbons with leaving groups to make nitriles. And nitriles, here's another way, alkyl chloride, backside attack, alkyl methyl sulfate, leaving group there. Secondary carbon with a bromine, better use a polar aprotic solvent here because secondaries are starting to get into the realm where the reaction is slowing down, and you're going to need a polar aprotic solvent. I used acetonitrile this time. And that brings to a close chapter 18. And we're going to start up with a good introduction, nice long segment for the most important reaction in organic chemistry coming up, called the aldol reaction. And I will see you very shortly.